Welcome to Understand the Math. This video is part of a series of videos on linear algebra and its applications and covers section 3.1 on calculating determinants. I'll teach you all about how to calculate 3x3, 4x4, and higher determinants using the cofactor expansion method, and also teach you how to calculate 3x3 determinants using the Rule of Sarrus, otherwise known as the shortcut method. Be sure to check out the link below for free guided notes that you can highlight and fill in as you watch this video. Let's begin by some real quick but very important basic information about determinants. A determinant is a real number. It provides important information about a matrix. The determinant of a matrix A is notated as det of A, or A with straight lines on the left and right sides. Determinants link together various concepts in linear algebra. Determinants are used widely in applications, and I've listed a few of them here. We're going to first review how to find the determinant of a 2x2 matrix, because when we compute determinants of 3x3 and higher matrices, part of the calculation will include calculating 2x2 determinants. The determinant of this matrix A is just equal to the main diagonal elements multiplied minus the off-diagonal elements multiplied. This gives us a formula for the determinant, and it's det of A is equal to A times D minus B times C. Let's walk through two examples where we compute the determinant. In our first example, we'll set the matrix equal to A, and then we'll write that the determinant of A is equal to the main diagonal elements multiplied minus 5 times minus 2 minus the off-diagonal elements multiplied, which is just 0. So our determinant is equal to a value of 10. Since the determinant of A is not equal to 0, we say that A is invertible, or also it's called non-singular. Let's now look at our second example. Just like we did in the first example, we're going to multiply the main diagonal and subtract off the off-diagonal. This gives us determinant A is equal to minus 63 minus a negative 63, which gives us a value of 0. In this example, our determinant is equal to 0, so we say that A is not invertible, and we call A singular. The determinant is a really nice way to find out if a matrix has an inverse or not. To learn how to compute determinants by cofactor expansion across any row or down any column, we'll first find the determinant of a 3x3 matrix using cofactor expansion across the first row. This will give you a sense of how cofactor expansion works before we get to the general formula. Since we're going to perform cofactor expansion across the first row, we'll highlight the first row of A, and then mark each entry in that row with an alternating plus or minus, starting with a plus in the upper left-hand corner. The determinant of A is then the first entry, A11, times the 2x2 determinant that remains after crossing out the row and column common to A11. We'll then subtract the next entry, A12, cross out the row and column common to A12, and this is the 2x2 determinant that remains. We'll then do the same thing with our last entry, A13, cross out the row and column common to A13, and this is our 2x2 determinant that remains. We're now going to use this formula to compute the determinant of these two examples. Let's start with our first example. We're first going to highlight the first row because that's the row that we're doing cofactor expansion along, and then we'll mark it with a plus, minus plus, Remember, you start with a plus in the upper left-hand corner. And now we can write down our formula. The determinant of A is equal to our first entry, 3. We cross out the row and column common to 3. That leaves us with a 2 by 2 determinant minus 4, 3, 4 minus 2. We then subtract off our next entry, cross out the row and column common to that entry, and then we write down the 2 by 2 determinant that remains. So that's minus 2, 3, 5 minus 2. And then we add our last entry, which is 2, cross out the row and column common to that entry, and we end up with a minus 2 minus 4, 5, 4. Now all we need to do is calculate our 2 by 2 determinants. This is going to be 3, 8 minus 12. Remember, it's the main diagonal elements multiplied minus the off diagonal elements. And then we have a minus 1 times 4 minus 15. And then we have a 2 times minus 8 plus 20. This gives us minus 12 plus 11 plus 24. And this gives us a value of 23. So the determinant of A is equal to 23. Now let's look at our second example. I would suggest that you stop the video and see if you can do this example on your own. Remember, we're going to be doing cofactor expansion across the first row, and you need to start with a plus, minus, plus. Our determinant A is going to be equal to 2 times 1, 2, 3 minus 1, minus a negative 2, times 3, 2, 1 minus 1, and then adding 3 times the determinant 3, 1, 1, 3. After you do this enough, your eyes are going to automatically just cross out the row and column that you need, and you'll be able to do it a lot quicker. This gives us 2 times minus 1 minus 6, which is minus 7, plus 2 times minus 3 minus 2, which is minus 5, and then plus 3 times 9 minus 1, which is 8. This gives us minus 14, minus 10, plus 24, and we get a value of 0. Let's now learn how to compute the determinant of a 3 by 3 matrix using the Rule of Sarrus, otherwise known as the shortcut method. This method is just a mnemonic device for computing the determinant of a 3 by 3 matrix. I want to caution you, this method only works for 3 by 3 determinants, and you can't use it for a 4 by 4 or higher determinant. To compute the determinant, we're going to write the first column and then the second column to the right of our matrix. And you want to make sure to write neat with this because we're going to be using diagonals, and neatness really helps. Now what we're going to do is we're going to multiply the entries along these diagonals, starting with the upper left and going to the lower right. We'll then multiply our diagonal elements the other way, starting with the upper right and going to the lower left. The multiplications that I've highlighted in blue get a positive, and the multiplications I've highlighted in pink get a negative. Our first multiplication is 3 times minus 4 times minus 2, which is a 24. Our second multiplication gives us a 15. We're just multiplying all three numbers. And then our next one is going to be minus 16. Now we're going to go back the other way. We're going to multiply 1 times minus 2 times minus 2, which is a 4, but we have to put a negative with it. Then we're going to multiply 3 times 3 times 4, which is a 36. That also gets a negative. And then our last one, we're going to multiply 2 times minus 4 times 5. That's minus 8 times 5 is minus 40, but it gets a negative. So we have a minus 40. This gives us a value of 24 minus 1 and a final answer of 23. This is the same determinant that we computed above in example number 1, and I did that on purpose so that you can compare the two methods and see the difference in the number of calculations that each method requires. Now that we have a general sense of how cofactor expansion works, I'll show you the formula for computing the determinant of an n by n matrix using cofactor expansion. When we use cofactor expansion to calculate the determinant of a square matrix, we can expand along any row or down any column. We'll multiply the entries of a matrix along a row or column by their respective cofactors. Let me now tell you what a cofactor is. A cofactor is the product of a sign factor, that means either a plus or minus, and the determinant of the smaller matrix formed by removing the row and column of the entry associated with it. I'm going to begin by first giving you the formula for using cofactor expansion to compute the determinant of a 3 by 3 matrix. When we do cofactor expansion, we can expand across any row or down any column. If we expand across the first row, the determinant of A is going to be A11 times its cofactor C11 plus A12 times its cofactor plus A13 times its cofactor. Let me show you what one of these cofactors looks like. C11 is going to be minus 1 to the 1 plus 1. That's the sign factor. The 1 plus 1 comes from the subscripts of C, and the sign factor is then multiplied by the 2 by 2 determinant that remains when the row and column common to A11 is crossed out, and those are the entries that remain. Let's now calculate the determinant if we expand down the first column. Our determinant is A11 times C11, and then going down, we get A21 times C21, and then the last term is A31 times C31. Let me show you what C21 looks like. It's equal to minus 1 to the 2 plus 1. Again, the 2 plus 1 comes from the subscripts of C. We cross out the row and column common to A21, and then these are the terms that go into our determinant. Let's now look at the formula we would use to find the determinant of an n by n matrix using cofactor expansion. Similar to our 3 by 3 example, if we expand along row I, our formula looks like this. Notice that each subscript has an I, and then the second subscript goes from 1 to n. If we expand along column J, the formula for our determinant is this, and the first subscript goes from 1 to n, and the second subscript is just j. The general formula for the cofactor, Cij, is just minus 1 to the I plus j times Aij. Minus 1 to the I plus j is our sign factor, and A sub ij is just the determinant obtained from A by deleting the ith row and the jth column. Let's now go back up to our 3 by 3 example and look at this sign factor. The sign factor for A11 is going to be minus 1 to the 1 plus 1, which is plus 1, and we can label A11 with a plus. A12 is going to be minus 1 to the 1 plus 2, which is minus 1, and we can label that with a negative. If you continue this calculation for all of these entries, you'll get the alternating plus-minus pattern that looks like this. Notice that if you go across a row or down a column, the sign is going to alternate. Students often prefer to remember this pattern rather than calculating the sign factor. I want to tell you one last thing before we walk through some example problems. When doing cofactor expansion, the best strategy is to choose the row or column that has the most zeros to expand along. This will simplify the calculations because you'll have less determinants to calculate. We're now going to walk through 3 example problems where we'll compute the determinant of a 3x3, a 4x4, and a 5x5 matrix using cofactor expansion. Let's start with our first example. You might notice that there are no zeros in this matrix, so we can expand along any row or down any column. Just to give you some practice, I want to expand down a column, and I'm just going to choose to expand down the first column. Before we begin the calculation, I'm going to do the plus minus. Starting in the upper left hand, I put a plus, and then a minus, and then a plus. Our determinant of A is then plus 3 times the matrix that remains when we cross out the row and column common to 3. This gives us the determinant minus 4, 3, 4, minus 2. And then we have a minus 2 going down to the next term. We'll cross out the row and column common to that term, and we have a 1, 2, 4, minus 2. And then our last term is plus 5. We'll cross out the row and column common to that one, and our determinant is 1, 2, minus 4, 3. This gives us 3 times 8 minus 12, plus 2 times minus 2 minus 8, and then plus 5 times 3 plus 8. This is minus 12, minus 20, plus 55, and when you add all those up, you end up with an answer of 23. Let's now look at our second example. This example is a 4x4 determinant, and we can choose which row and column to expand along. When you look at this matrix, notice that the third row is the row or column with the most zeros. So that's the one I'm going to choose to expand along. Let's now write our plus minus. In the upper left, we have a plus, minus, so then 3 is a plus. Our determinant of A is going to be 3 times the determinant that remains when we cross out the row and column common to 3. And that's going to be 0, 0, 5, 7, 2 minus 5, and then 3, 1, 7. Now we have to choose what row or column to expand along for our 3x3 matrix. You might notice that the top row is the row or column with the most zeros, so that's what we're going to expand along. Our plus minus starts all over again. We start with the upper left, and we do plus, minus, plus. This gives us 3 times 5, and we cross out the row or column common to 5, and we're left with a 2x2 determinant, 7, 2, 3, 1. This gives us 15 times 7 minus 6, which gives us a final value for the determinant of 15. Let's now look at our third example. This is a 5x5 determinant. Let's first look for the row or column with the most zeros. You might notice that the second row or the second column have the same number of zeros. So we can pick to go along a row or go down a column. I'm going to choose to go along a row just because my eyes work better going from left to right rather than up and down. We start our sign pattern in the upper left. So this is plus, minus, plus, minus. You can go along any row or down any column to do that plus minus to get to the entry that you need to. Let's now cross out the row and column common to 2, and we're ready to go. Our determinant of A is going to be minus 2, and then we have a 4x4 left over. This is 4, 0, 3 minus 5, 7, 3, 4 minus 8, 5, 0, 2 minus 3, and then 0, 0 minus 1, 2. Now let's look and see to find which row or column has the most zeros. Our second column is the one with the most zeros, so that's the one we want to expand along. We start our plus minus again. The plus goes in the upper left, minus, plus. Let's cross out the row or column common to 3, and we can begin our calculation. We have a minus 2 Now we have a 3, and then the 3 by 3 determinant that remains is 4, 3 minus 5, 5, 2 minus 3, and then 0 minus 1, 2. Again, we look for the row or column with the most zeros. It looks like the third row or the first column has the most zeros. I'm going to go down the first column because I think it's easier to start with the upper left. Our sign pattern is then plus, minus, plus. We don't really need the plus with the 0, but I just put it. Now let's begin our calculation. We have minus 6, and because we have 2 entries that are not 0, we're going to have 2 determinants. So we'll do a bracket here. Our first one is going to be 4 times the determinant that remains when we cross out that row. So this is going to be 2 minus 3 minus 1, 2. And then we have minus 5, and the determinant that remains there is going to be this one, and that's going to be 3 minus 5 minus 1, 2. This gives us minus 6 times 4. This determinant is going to be a 4 minus 3, which is 1. And let's go ahead and let's do this one. This is a 6 minus 5, which is also a 1. So we end up with a 4 minus 5 for a final answer of 6. Finding the determinant of these larger matrices just takes a lot of practice, but you can definitely do this. The last topic that we're going to go over is how to find the determinant of triangular matrices. In section 2.3, we looked at 3 types of triangular matrices. We had an upper triangular matrix, we had a lower triangular matrix, and we had a diagonal matrix. The determinant of a triangular matrix is the product of its entries along the main diagonal. Let's walk through some example problems to see why this is true and to see how it works. I'm going to compute the determinant of this first matrix by doing cofactor expansion along the first column because that has the most zeros. This first term will be a plus. We have determinant of A is equal to A11 times the 3 by 3 determinant that's left. This is A22, A23, A24, 0, A33, A34, and then 0, 0, A44. Let's now do cofactor expansion along the first column again. This gives us an A11, A22 times the 2 by 2 determinant, A33, A34, 0, and A44. This gives us a final value of A11, A22, A33, and A44. Notice that our answer is just the product of the entries along the main diagonal. Let's now look at our second example. It's a lower triangular matrix, and we're not going to go through the derivation on this one. We're just going to remember that the answer for the determinant is the product of the entries along the main diagonal. So we have determinant of A is just 1 times 3 times 6 for a value of 18. Our third example is a diagonal matrix. So again, just like the second example, our answer is just going to be a product of the entries along the main diagonal. So it's going to be 1 times 7 times 4 for a value of 28. These examples show us that if you have an upper triangular, a lower triangular, or a diagonal matrix, you can find the determinant by just multiplying the entries along the main diagonal. Be sure to check out the next video in this series, where I'll teach you all about the properties of determinants and how to calculate determinants using the row reduction method. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.